We are going to now think about bonding, how electrons will behave if they have any sort of interaction between different nuclei. So there are kind of two extremes and maybe three ways that you can think about bonding. The first way is that the electrons between two different nuclear centers are being shared. So this kind of looks like a linear combination of the two orbitals that you started with. If these were like two hydrogen atoms that bonded together, then they would have started off with two s orbitals. There would be a probability density or a wave function that describes what likelihood the electrons will be at any given point around the nucleus. And they look kind of like balls. If you were to like truncate the like draw a perimeter around 80% probability of where the electrons are, or 90% probability, it would look like a sphere. And if you have bonding, well, the bonded electrons, they're going to end up being equally distributed around each hydrogen. A lot of the time, those electrons are going to be in between the hydrogen nuclei. Sometimes they'll be on one side, sometimes they'll be on another side of either nucleus, but for the most part they're going to be in between. So this is how you think about them, and this is actually called a molecular orbital, or MO for short, instead of an atomic orbital. We're not going to cover that in this class really much at all. Drawing these things is going to be more stuff you see in the next chemistry course, Gen Chemistry, but for our purposes it's good to know what these things are and what the different kinds of bonding mean for different molecules or different compounds. What's the other extreme? So this was sharing of electrons. This is borrowing or taking of electrons. So if we had two atoms that were neutrally charged and one of those atoms takes an electron from the other, then the atom that gained an electron will become a negatively charged ion or anion. So it would have like an extra electron or multiple extra electrons. And the atom that lost an electron or lost multiple electrons would have a positive charge or a multiply positive charge, like 2 plus, 3 plus, etc. And it would be called a cation. So these two ions do not share electrons. There's no shared electrons. There's no overlap of their atomic orbitals. What's happened here is that an electron's been stripped from one and is now being held by another. And they're not being held together by electrons that want to be in between two positive centers. They're being held together by a difference in charge. The positive charge of the cation and the negative charge of the anion will attract each other, just like opposite poles of a magnet will attract each other. So this is an electrostatic interaction. It's positive and negative charges interacting that make them come together or make them like not move terribly apart. And that attraction is weaker than this one. The covalently bonded molecules tend to be more strongly held together. It's harder to break a bond like this than it is to break a bond like this. Water will dissolve this kind of a bond. Water really doesn't dissolve this kind of a bond much at all. Like, it's unusual for that to happen. It happens only in very special cases, and it's not really dissolving. It's stuff like this being broken by water molecules that are forming other bonds like this. So I don't want to confuse you too much. The point is, water just acting with dipole-dipole forces that we'll cover later can break these apart without any sort of without any sort of like meaningful chemistry going on, versus this thing needs chemistry to be broken apart, for sure. Like, I would call anything that can break this apart some kind of chemistry. I would not hesitate to call it this. The electrons would have to be dissuaded from being in this sort of orbital for this bond to be broken, and this requires no change in electrons for this to be broken apart. So in the sense, as I told you at the beginning of the course, the essence of this class is what's happening in valence electrons. There's not really any necessary change in valence electrons for a positively charged and negatively charged anion to be pulled apart. But there does have to be a change in bonding electrons, or like how those valence electrons are being bonded together or participating in bonding before you actually can see this bond be broken apart. Okay, so we got these two extremes: equal sharing, borrowing or theft, no sharing, and then you could have what's called a polar covalent bond. So the sharing thing was called covalent bonding. Ionic bonding is when you have borrowing and no sharing or theft. And here you have something in between where there's unequal sharing. That's called polar covalent bonding. There's still sharing of electrons, but there is a unequal sharing where one of the nuclei is hogging the electrons. The nucleus that is hogging the electrons is going to have a partial negative charge. That's what the delta means. It means partial. And the nucleus that has less of the electron around it, less electron density around it, is going to have a partial positive charge. So it doesn't completely lose an electron, but it does have less of the probability density around it. And if you want to think about this in classical physics terms, you could say that the electron spends less of its time around this nucleus, it spends more of its time around this one. So on a time averaged basis, this thing has more of a negative charge, this thing has a partial positive charge, but not a full charge difference. So the charge difference here is a full electron difference. There's not a full electron difference here. Okay. And this is more of a continuum than I think about it as. So if there's an electronegativity difference between bonding atoms, if there's a very, very, very large electronegativity difference, like if we're talking about a metal and a non-metal involved in a compound together, you would expect that to form some kind of some type. You can figure out what the charges are later, but you would figure it out that there'd be some kind of ionic compound that you'd form from that. A metal and a non-metal, going to be ionic in character. That's a huge electronegativity difference. The metal is very not electronegative, it's electropositive if you want to call it that, and the non-metal is much more electronegative. So that's going to give us an ionic bond. On the other extreme, you could have two atoms that are both non-metals that are actually the same element. Like you could have two nitrogen atoms. They are going to bond together through covalent bonding because their electronegativity difference is 0. They're the same element. They have exactly the same electronegativity. You could have some sort of intermediate situation like water, where there's a hydrogen that's less electronegative and there's an oxygen that's more electronegative. So the more electronegative oxygen is going to hog electrons in the covalent bonds. Electronegativity, is, as I mentioned last time, has to do with the ability of a nucleus to attract electrons in a bond, in a covalent bond. So what that means, we actually broke this down into a more basic idea of electrons being attracted to a nucleus. And we were saying that atoms or elements in the periodic table that are up and to the right had a higher electronegativity because they would hold their electrons more closely. So that attractiveness of the nucleus as being seen by the outermost electrons is the same attractive force that's going to be leading to higher electronegativity, higher ionization energies, because ionization energies are how much energy it takes to pry that electron out of those outermost highest energy orbitals and away from the nucleus. And the electronegativity is how much those electrons that are being shared are attracted to that nucleus. So it's really high energy electrons around the nucleus. How attractive is that nucleus? How attractive is that nucleus even after you think about all the other electrons that are lower energy that are shielding that nucleus? So it leads to several phenomena, including electronegativity, including ionization energy, including the size of the atom. Like if the outer electrons are more attracted to the nucleus, they are going to be held more tightly and more closely to the nucleus. So as you get higher in the periodic table and to the right, you should be seeing smaller atoms, more electronegative atoms, and higher ionization energies. All because the outer electrons in those elements are more and more attracted to nuclei that either have the outermost electrons in smaller orbitals or have higher effective charges because of only partial shielding by an extra electron for every additional proton that you get by moving from one element to another in the periodic table across a period, across a row.